This video, we are going to look at greedy algorithms from a theoretical point of view. So what we are trying to do here is that we want to figure out when greedy algorithms work. In other words, under what conditions, rather than each time we have to prove a greedy choice works, we want to figure out what type of optimization problems and in what conditions, and we will know that the greedy choice always works, so that we don't have to prove the greedy choice each time. So first we're going to look at independent systems. All right, so now let's look at this slide. We want to figure out exactly when a greedy strategy does produce optimal solution. And of course, we know that for optimal solutions, we can either look at maximization or minimization. We know that if we want to maximize an objective, it's equivalent to minimize the negative of that objective. It's convenient to look at maximization first. We define an object called independent system. Suppose we are given a finite set of elements, okay, we call it E, and then we also have a collection of subsets of E, and we call it I. So this is a curly I, so that stands for independent system. So now, first of all, let's look at what we are given. So what we are having here is we have a set E, so which is a set of any elements, and then we have a set I. So this I is a collection of subsets, so which means it is a subset of the power set of E. Power set of E is all subsets of E, and then I is simply a subset of that. So then these two things, E and I, we are going to call it an independent system if E is closed under inclusion. Meaning, if A is in I, then B, and B is a subset of A, then B is also in I. So what that means here is that, for instance, we know that I is a subset of I is a set of subsets of E, which is a subset of power set of E. And then if A is in, let's say A, right? So it contains several elements, and let's say this is in I. And then any subset of these A, for instance, A1 and A2, it is a subset of A, then we know that A1 and A2 as a set is also in I. That's what it means by closed under inclusion. Okay, so this is what we have. Now let's look at some examples of independent system. Example 1, let E be any set of vectors in some vector space. So it's a set of vectors. And I is a collection of sets of linearly independent vectors. Let's say we have a vector, we call it V1, V2, let's say Vk, and these vectors are linearly independent. What it means is that so if you look at this equation, linear equation, and so let's say this is equal to 0. Of course, this is a vector 0. Then we must have A1 is equal to A2 is equal to AK is equal to 0. You look at any of these subsets, like so if V1, V2 up to Vk are linear independent, V1 and V2 is linearly independent, because if it's not, then of course it would violate this condition. So similarly, V2, Vk, or V1, V2, Vk, right? So these, any subsets of these vectors are linearly independent. If you just look at one, since it's linearly independent vector, we know that it's not it's not 0. Zero here. Or just, it's not 0. So if you want A1, V1 to be 0, then A1 has to be 0. Hence, if you look at E, which is a set of vectors, and I, which is a set of linearly independent vectors, we know it is an independent system. So next example, let's look at graphs. Let's say we have an undirected graph. E is a set of edges, and I is the collection of all acyclic sets of edges, which means that this set of edges do not form cycles. Okay? Then, of course, any edges in this set of edges, they don't form cycles either. So that really means that it is closed under inclusion. Hence, this EI is also an independent system. The next example, let E be the set of edges of an undirected graph, same as example 2. And I here is the collection of sets of independent edges. Independent edges means that they don't share a vertex. For instance, this is an edge. This is another edge. Then these two edges are independent. But if you have this edge and then there's another edge, then these two edges are not independent because they share the same vertex here. So you look at a set of independent edges, then any elements or any edges in this set, they must also be independent. Hence, it is an independent system. The next example is from activity selection. So let E be the set of all intervals Si and Fi. So Si is the start time of activity I, and Fi is the finish time of activity I. And this curly I is a collection of subsets of non-overlapping intervals. So in other words, they are compatible activities. Okay, so non-overlapping. Then given a set of non-overlapping intervals, then any subset of this set is also contain non-overlapping intervals. Hence, it is an independent system. So this EI is an independent system for permissible activities or for compatible activities. Okay, so for this independent system, we can look at the following problem, which is called maximum independent subset, or max ISS. Given an independent system, so what are given? So this input is an independent system. Then what we really want to find is we want to find an element in this curly I, so we call it I, such that C of I is maximal. So this curly I has many subsets. I want to find one. Either, of course, it has the largest number of elements in it, or under certain cost measure, I want, or under certain measure, C, I want this C of I to be maximized. C here is a profit measure, okay? We may want to use P, but anyway. So this is a profit measure. And then we can use a greedy algorithm to find a such I. So what we're going to do is to sort elements of E according to this measure C in non-increasing order. Without loss of generality, we just simply assume that C of E1 greater than or equal to C of E2, and so on, greater than or equal to C of En. The greedy algorithm is the following. So initially, we set it to empty set. And then for each of these E, starting from 1, we are going to see whether I adding this EI, I get a element in this curly I, in this independent system. If it is, we put this EI in it. Okay, starting from C of E1, and then starting from E1, and then E2, and then En. So each time, if I add these new elements, I get a set in this curly I, then I will include it. And in the end, I found an I and I returned it. It's a greedy algorithm. How good it is? How good is this greedy algorithm? So obviously it finds a I. Okay, so then now we want to figure out how close is this set we found. How close is it to the optimal or to the maximal solution? So let's look at the following measure. So we let F be a subset of E, and then a set I, which is a subset of F, is maximal independent subset of F if no independent subset of F contains I as a proper subset. So now, first F is a subset of E because any elements in I has to be a subset of E. And then I'm going to say, but I don't know whether this F, so I don't know whether F is in curly I or not. But if there is a set I, which is a subset of F, and I could be in I, right? So this is possible. Then we're going to say it is the maximal with respect to F. So let me just put it here that, so this is F, and this is I. So I here, I know is included in this independent system. So this is a maximal, which means that for any other sets that includes I, also a subset of F, let's say for any one of these, okay, it's not going to be in I. So this is the largest one. So this I is the largest one. Then we can define two measure. So we call it U of F and V of F. So U of F is the minimum. So this is size of maximal independent set of F. Okay, so we pick the size to be the minimum one. So which means that so given F. So let me explain it here. So given F right here. So you have an F. Okay, so you could have I, this is a maximal, maybe another I, so this is I1, I2. So any set includes I1 as a proper subset is not going to be in I. This any set includes I2 as a proper subset is not going to be in curly I, right? Maybe you have another one here, I3. So they are maximal independent subset of F. I pick, so obviously in this case, I3 has the smallest size. So the size of I3 then is UF. Okay, that's what it means. And then let's look at VF. So VF here is I is an independent subset of F. And then you take the maximum one. This has to be a maximal subset of F also, because you take the max. Okay, so you have all of these, then of course these looks like this is bigger. So this I2 will be VF, right? So this in this case, UF is I3 smaller. I2 is bigger than I1, so this is a VF, which is I2. So we let I sub G be the solution obtained from the greedy algorithm we explained earlier, we looked at earlier, right? So we just list all the elements according to its profit measure in non-increasing order. We following this order, we look at each element and add it to the previous set reconstructed to see whether this set is in I. If it is, we add it in. Okay, so that is the greedy algorithm. So let's say this is the solution. We got a solution from the greedy algorithm. So it has a maximized maximum solution. Let's call it I star, which is what we are trying to find. But the greedy algorithm finds IG. Now then, I want to know how close is IG to I star in terms of the cost. So that means we want to know how close of C of I star to, or how close of C of IG, because this is the solution from the greedy algorithm, how close is to it. Now, this is a maximized, so that means C of IG cannot be greater than, strictly greater than C of I star. So if I take the ratio C of I star over C of IG, then it will be greater than or equal to 1. So this is straightforward. But the other direction is, which is interesting, is the other direction says that this ratio is actually less than or equal to the maximum size of independent subset of F over minimum size of maximum independent subset of F. So this is for all F, which is a subset of E. Lower bound is straightforward, and then the upper bound, we have this. So as you can see here, if this V of F is equal to U of F, then C of G is equal to C of I star, which means the greedy algorithm actually produces the optimal or maximal solution. Okay, now let's look at how to prove this result. So we let this E be the set of elements according to their measure C in non-increasing order, which is E1, E2 up to En. So, and then we look at, so at the ith iteration, this is the what the elements we're going to look, or we have looked when we reach at the ith iteration. So as we let this set I sub I be this EI intercept IG. So what that means here is that so at the ith iteration, this is what the elements I have looked at. Some of them will be included in IG, some of them will not be. So I am looking at everything that's included in IG, and I'm going to call it I sub I, which is independent because this is how we are going to include something into IG. So it is independent, but then we're going to show that it is maximal independent subset of EI. So we're going to prove it by contradiction. if it is not maximal, that means I have an independent subset that includes I sub I as a proper subset. What that means here is then I will have something in this EI that is not included in IG, but it is independent. When I put this element into I sub I, it will be independent. So this is what this assumption, if it's not maximal, this is what we get. Okay, then we are going to look at the set I, which is actually at the beginning of the J's iteration, so which will be, so this I is actually I1 at the beginning of J's elements. Okay, then this EJ, I'm sorry, this I sub J minus 1 is, of course, a subset of IG because this is what we already have included in IG, right? It's a subset of IG. So then I put this EJ into it. And because this I sub I is also everything in IG, right? So it's everything in IG. So this is also in IG. So then I put this EJ in it. It will be included in IG. So this I will be a subset of I sub I, and then put it in here, adding these new elements. So we know this is independent because by assumption it is independent, right? So then any subset of it will be independent. So it is independent. So when it is independent, that means this EJ will be included in IG, but here you're saying that this E sub J is not in IG. So that's a contradiction. So the contradiction then gives us the following. That means that it is maximal. So that means now, at least now I know this size of I sub I is a upper bound of U. So U of EI, it is a minimal size of a maximal independent subset of EI. So then of course, this is one of them, is one of the maximal. So this is minimal. So it has to be less than or equal to this. And then since this EI intersect I star, EI of course, it is a subset of I star, so it is independent. Then I have a lower bound of V of EI because this is the maximum size of independent sets. So then it is one of the independent sets. So then of course there's a V of EI is greater than or equal to this. So now from I from 1 to n, okay, so we look at the difference. They could either be equal or they could be different by 1, right? Because we just, each time we add one element to it. So then we can have, if EI is in IG, which means that EI is included in IG at the I's iteration, which at the I minus 1 iteration, and earlier this EI has not been looked at. So if it's in IG, it's equal to 1, otherwise it is 0. Let me go back here to add something. So we know this J, this EJ is in EI, so which means this J is less than or equal to I. So now we just, hence this I sub J minus 1 has to be included in this, okay, I sub I, because it is, J is less than or equal to I. So because of this, all right. So then this EJ then will have to be included in IG, so which is a contradiction. So now we do some manipulation by looking at C of IG and C of I star. So this is the maximum solution. This is the greedy solution. So we know that we just add them up for all elements in IG. So then because we define this difference, okay, so it is actually equal to this, right? So then we can write it up by doing some merging. So I will include C of EI minus C of EI plus 1. And then this is the last one. Okay, so we know this part is greater than or equal to 0. And from earlier, we know this has a lower bound, U of EI. So this is U. So then we have this. Okay, similarly, this is a lower bound. So we have that. And for C of I star, so we just follow this by replacing I sub I with I sub I star. Okay, so this is straightforward up to this point. So now we let this ratio that we're going to get, V of F, which is the maximum size of independent sets of F. This is the minimum size of maximum independent set of F for all F. So that is R. So then since this is for all F for a particular F, which is EI, which is a particular F, because this is the maximum, so it cannot be greater than R, right? So this ratio cannot be greater than R. So we know this is less than or equal to V of EI, right? So we can, then it's less than or equal to V of EI. And then V of EI is less than or equal to R times U of EI. So we take the R out. What's remain is less than or equal to C of IG, because this whole thing is less than or equal to C of IG. Hence, we prove this result. From here, then we know that if for any F, which is a subset of E, we have V of F is equal to U of F, then IG is I star. Okay, so from this result. So then we can define a new concept called majoid. A majoid is an independent system such that, so EI, such that for any F, which is subset of E, V of F is equal to U of F. So here's each element is considered equally likely. And weighted majoid, W of A is equal to all the elements in A, you sum up their weights. Now let's look at an example of some majoid. So we have a graph majoid. So for a given graph G, let E be the set of edges. And here I, the family of edges that form an acyclic subgraphs of G. Acyclic means they have no cycles. Then it is then E comma I is a majoid. Okay, so the proof is this. Okay, so for any F, because F, now E is a set of edges. So for these set of edges, we can define a graph, right? So only the edges in F is in the graph. Okay, so then this is a new graph, and this new graph could have several connected components. So which means that it could be a component, which means every pair of nodes here will have a path that connected them. And then you may have another one So every pair of nodes will have a connected path. But between these two, there is no path. So this is two components. So this is connected, but between these two, there is no path. So this graph by itself may be connected, but of course it can only be can be divided into a bunch of connected components. So let's say we have m of them. Then the maximal acyclic subgraph is a spanning tree. Then, of course, for the spanning tree, it has exactly this many edges. And then for altogether, the maximum acyclic subgraph for this graph, the spanning tree, then, of course, add them together will be V minus M edges. Okay. So that's U of F is equal to V of F for any F. Okay, so it is a matroid. Example 2. So let E be a finite set, and then given a subset A of E, we let C sub A be the set of all subsets of E such that A is not a subset of B. So we have A. Okay, A is a subset of E, and then for any B, so this is B, A is not a subset of B, right? And so you don't have anything that includes A. So anything here or touch it, these are all possible B's. Okay, you include all of these B's, and then I call it CA, but not this one. This is not. Right? A is a subset, so this is not. So not, this is not. Then we're saying that this is a matroid. So here's a proof. So let F be a subset of E. If A is not a subset of F, okay, then F is in CA, and so F is independent, which is also maximal, because if A is not in F, okay, so first, of course, F is one of these B's, so we know that F is in CA because A is not subset of this set. So, and then because we want to find U of F and V of F, so we know that for any such B, is a subset of such a B also satisfy this condition. So then, of course, we know it is independent. And because we are looking at this F is already itself, so it has to be the maximal, right? So we are not looking at any subset of F. So if the F itself is independent, so F has to be maximal. So that means U of F is equal to V of F, which is just the size of F. Okay, so for any of these. So then the other case would be A is a subset of F. In this case, then F is not independent. It's not in this CA. Okay, F is not in the CA. But by getting rid of one element, so every maximum in the subset of A must be in the form for some element in A, I just get rid of it. Okay, then I minus that element in A, so then this will be in CA. So it is maximal because I just get rid of one element. So this is not, but by getting rid of one element, it is independent. So that means in this case, UA is equal to VA, which is F, size of F minus 1. Hence, it is also a matroid. Now let's look at a example of activity selections. So we know that it is independent, right? So earlier we looked at activity selection if I is a collection of all subsets of compatible activities, it is an independent system, but it is not a majoid. So when we want to say something that's not an independent majoid, we just need to find a counterexample. So here's a counterexample. So we let E be a set of activities. So this is the start time, finish time, start time, finish time, and so on. And then we let A be 1, 6. So then B, okay, obviously is the maximal because the whole thing, so A is in I and B is in I, and both are maximal, right? Because this maximal means that anything that contains A as a proper subset, so A is 1, 6, that includes all of these times, so they cannot be compatible. But these are compatible, 2, 3, 3, 4, 4, 5. So it is also maximal. There is nothing else that include them can be independent. So both A and B are maximal. They are compatible and they are maximal. Okay, but in this case, that is not a majoid because there's only one element in A. There are 3 in B, and they are not equal. There's a maximum with maximals not equal. Okay, so it's not a majoid. Next, we're going to see this result. An independent system E comma I is a majoid if and only if for any cost function C, the greedy algorithm for max ISS produces an optimal solution for any instance. Okay, so this is actually what a majoid comes from, right? When UF is equal to VF. So intuitively, it's clear. So we're not going to go through the proof. Instead, we are going to the next slides. So by the definition of the majoid, an independent system is a majoid if and only if all maximum independent subsets have the same size. Hence, an independent system is a majoid if it satisfies the following exchange property, which we can use to help us determine if an independent system is a majoid. So which means that if A is included, if A is an element of I, which is, now remember, this is A is a subset of E. B is also in I. Now both A and B are subset of E, and the size of A is less than size of B. Then there must exist an element in B, but not in A, such that by putting this E into A, we get a new element in I. Okay, if this is true, then this independent system is a majoid. Next, we are going to look at a minimization problem. So for this, we are going to make this, so first let's look at this slide. So we know for maximization, for independent subset systems and matroids, we have these greedy algorithms. But for minimization, we don't have anything that is similar to maximization, but we have something called submodularity. So we let F be a function from a power set of E, which means it maps a subset to a real number, a positive number. Then we say function F is submodular if for any subsets of E, A, and any B, which is subset of E, which means they are elements of power sets, we have this, okay, F of A plus f of b. Now remember, it gives you a positive real number, which is greater than f of a union b plus f of a intercept b. So if this is satisfied, then this function is called submodular. Okay, then we can look at a minimum set cover problem. Given the collection C of subsets of set E, okay, we find a subcollection C prime of C. So this is what we want, with minimum cardinality such that every element of E appears in a subset in C1. So that means that we have a minimum set cover. So we have a set E, which has a lot of elements. And then you may have a subset of this. You may have a subset of that, subset of that, and subset of that. So they cover E, right? So each element E in E it appears in one of these. But I want a subcollection C prime, such that it has the smallest number of subsets in it, numbers in it. So obviously, in this particular case, for instance, if I pick this one and pick this one, then it covers E, right? So it has a smaller, so it has the smallest number. So this is C prime. It's just these two, okay? Original C is 4 of them, right? So that's what we want to find the smallest number. Now, for a subcollection A of C, okay, so it's a which means it's a subset of C. We define that this function f will be the size of all the elements. So for any element which is a subset, okay, so we take the union of this subset, we take the number of elements of this union, then we call it f of A. And verify, okay, so this is true. F of A plus F of B is greater than or equal to F of A union B plus F A intercept B. So this is submodular. In order to find this C prime, this is a greedy algorithm. So initially A is, or C prime, right? But initially A is empty set, and then while that this f of A does not cover E, which means that it's less than the size of E, we simply choose S in C such that when we add this S to A, this F gives me the maximum value. Okay, we choose that S, and then we put this S into A. So that is the algorithm. Now let's, take the analysis. Suppose that S1, S2 up to Sk are selected by the greedy algorithm in this order. So we first pick set S1 and then pick S2 and so on. Then we let this Ci be up to, from S1 up to Si. Then F of C sub I plus 1 minus F of sub Ci is greater than or equal to. So this has not been covered. So anything that has not been covered over a optimal solution. So then what we want to know is that what is the upper bound of K? Okay, so we can show that this upper bound of K is less than or equal to optimal solution times 1 plus log of gamma. Gamma is the maximum size of this Si. Hence, because it could be at most n. So that means that we have the upper bound of this K will just be, you can think of it as a optimization ratio. So that's log n plus 1 is the optimization ratio. So what is the meaning of the submodularity? The meaning of it is the earlier the better. Okay, and then monotone increase in gain. Okay, so so that's so much for greedy algorithms.